In the plane of this page, a square metal loop with a resistance of 79 ohms is positioned near a straight cable that has a current of 6.8 amps, as can be seen in the above setup. If the loop is at rest, what is the induced EMF, electromotive force, in this loop? What are the magnitude and direction of the induced loop of the current? What are the magnitude and direction of the magnetic force on the loop? And repeat if the loop is moving to the right at a constant speed of 45 meters per second. In question B, find the electric power dissipated in the loop and show that it is equal to the rate at which the external force pulling it would be needed to keep it at a constant speed. Does work. Okay, so basic question we're asked here is electromotive force, induced voltage in this loop. So my first thought is we have a EMF, which is defined as negative d flux dt, which flux is the magnetic field times, actually it's a little bit more formal here, magnetic field dot area. And since the magnetic field due to the loop is kind of like this, it's going to be around it. Use the right hand rule, thumb in the direction of the current. At the loop, the magnetic field is going to be into the board. The area vector, which is normal to the surface, to the plane of the surface, is also going to be into the board, maybe out of the board. It doesn't really matter. Either way, these two are going to be parallel. So the dot product is going to be magnetic field times area. So we want to find magnetic field times area of our little loop up here. And I guess little is appropriate because it is 2.3 centimeters, which is about an inch in each direction. All right, so the magnetic field due to a line is going to be mu naught, which is 4 pi times 10 to the negative 7th, I, which is the current of the loop, over 2 pi r, where r is this distance right here. I'm going to call this distance our initial. I'm going to call this distance our final. So our initial is 9 centimeters. Our final is 9 centimeters plus 2.3 centimeters. Okay, that seems reasonable. And so to do this, though, the magnetic field at this point is going to be different than this magnetic field at that point. And the way we're going to find magnetic field times area is we're going to break this up into small little segments, and we're going to integrate. So integrate, I'm going to do this, call that dw, for width, a little differential of a width, times length. That's supposed to be an L for length. We're going to integrate this way. Therefore, I'm going to say that our magnetic field times area is going to be the integral from some r initial to r final of that magnetic field, which is mu naught I over 2 pi r times, I'm going to call this dA, where this dA is going to be this area here, this differential area. That differential area is going to be length times d width. And in this case, d width, since it's going to be in the same direction as r, I'm going to say that's the same thing as dr. I'm going to say that big R on the bottom, same as small r. R initial is 9 centimeters. R final, supposed to be an R. No, it looks kind of like an F. R final is going to be 9 centimeters plus 2.3 centimeters. And then I is going to be 6.8. I think it's 6.8 amps. And then mu naught is just a constant. Okay, so now we got that. Let's throw in some, not values, but I'll just rewrite it to something semi-reasonable. So I'm going to pull out the constants. They'll say mu naught I over 2 pi. R is not going to be pulled out because that's going to be a variable. dA is L dW, so I'm going to pull out the L. And then we're going to have an integral from r initial to r final of 1 over r dr. The integral of 1 over r becomes natural log of r. So magnetic field times area is going to be mu naught I L over 2 pi natural log of r final minus natural log of r initial. Okay, so this is our B dot A. Okay, seems reasonable. Seems reasonable enough. But we're not really interested in B dot A. We want the derivative of such. So the negative d dt of B dot A is going to be, so these are all going to be constant, mu naught I L over 2 pi. Now we just took the integral of natural log, so now we're going to take the derivative of it, which is just going to put it back to where it started. Now the caveat here is going to be, this is going to be 1 over Rf times dr dt minus 1 over r initial, again, dr dt. That's the chain rule. And probably do some little brackets here. So dr dt, in this case, is going to be v, small v, for velocity, not to be confused with voltage, which is the same as EMF. So, and they give us here 45 centimeters. So, the EMF, and I forgot the little negative sign here, what I could do is just, yep, I'm just going to leave it like that. EMF, so this is going to be mu naught I L over 2 pi times, I'm going to factor out this v, 1 over r final minus 1 over r initial. So our EMF, repeat if the loop is moving to the right at constant speed, blah, blah, blah. What is the, if the loop is at rest, what is the induced EMF of the loop? So the EMF of the loop is going to be this right here. And if it's at rest, then V equals 0. This whole thing just equals 0. It doesn't go away. So part 1, trick question, 0. And one way to think of that reasonably is the EMF induced is the change in flux with respect to time. The flux is the magnetic field through the area. And if it's constant with respect to time, then it's not changing. The only reason it's changing with respect to time is when it's moving, which means that the magnetic field is getting weaker the further away it gets from the wire. So magnitude and direction. So the magnitude, this will be the magnitude of the EMF. There's supposed to be a negative sign over here. The direction. So the easy way to think of this for the direction is, we'd probably do it with math. But we have a magnetic field going into the board. Its magnetic field, dB dt, is going down as the loop moves to the right. And so what's going to happen is the EMF induced, created, is going to oppose this change. And so it's going to create a magnetic field coming out of the board, like so, out of the board, to reinforce, to mitigate the drop in magnetic field because the loop is moving away. I know, it sounds really complicated, word salad. It is challenging. But that's the sequence of events and the best way to think of it. So what's going to happen is magnetic field coming out. To make a magnetic field going out, the current, using the right-hand rule, is going to have to go this direction. So wrap your fingers around the loop. Thumb points out of the board. That provides this for a magnetic field. That is going to be the direction of current induced. And that'll be, I guess, the direction of EMF. Yes. Direction of induced current in the loop will be counterclockwise. And the magnetic force on the loop, what is the direction and magnitude for force of a magnetic loop. The easiest way to think of this is the current carrying wires in the same direction attract, and current carrying wires in the opposite direction repel. We'll talk about that more, I think, in part C. But these two are going to repel. These two right here, close ones, are going to repel. These two are going to attract. But since the close one has a stronger magnetic field at it, that's going to be the dominant one, and so these are going to repel. So the magnetic force on the loop is going to be the direction of it is going to be to the right, and they want a magnitude as well. The easiest way to do the magnitude is, we'll talk about the magnitude in part C, I think. All right, so that is how we find the EMF, which is kind of the core of part B. So now for part C, in question B, to find the electric power dissipated in the loop and show that it is equal to the rate at which the external force pulling the loop constant speed does work. Okay, so we have, this will be answer to part B. For part C, we want to find power. So to do that, we're going to say that power is current times voltage. The little bars up there mean voltage, which is the same as I squared R, which is the same as voltage squared over R. Ohm's law. And so that's going to be EMF squared. Voltage and EMF are going to be the same. So this then becomes mu naught I L over 2 pi 1 over RF minus 1 over R naught quantity squared all over the resistance. Did I forget a V? Yep, there's supposed to be a V in here too. V. V for velocity. So, yes, I'm good with this. So that is the power dissipated by the circuit due to the current flowing. And we found that by finding the EMF, which was the change in magnetic flux times area. So now they want us to do it a different way using force. So the idea with the second part, the external force, is that this wire is going to create a magnetic field, like so, and that's going to influence this wire, and that's going to influence that wire. So we have a couple formulas we can think of here. So force equals QV cross B, which is equal, so another way of looking at this is if you take, velocity is in meters per second. If you take the per second and move it under the charge per second is basically current. So this is similar to I L cross B. The B is into the board. The L is this length of wire right there. Therefore, the cross product is just going to be ILB, where a cross product is a measure of how perpendicular two vectors are. So force equals ILB, and then we want to find what I is, this current. So current is LVB. This can be derived using the d flux dt that we did earlier, but it's something that a lot of people have memorized. The L is going to be the length of these vertical sides here. So I equals LVB, Ohm's law, current equals voltage over resistance, which is EMF over resistance. So this, so I'm going to say, we write this as EMF equals, move this out of the way so we can actually see it. EMF is current times resistance. So little arrow EMF, IR equals LVB. Therefore, current equals LVB over resistance. Okay, so now we're going to combine these two formulas that we just put up right here, and we find that the force equals I, which is LVB over R, times LB. This now gives us L squared B squared times small v velocity over resistance. Now, we're not interested though in the force, we want to know the power. How did they phrase this? The electric power dissipated equal to the rate of which an external force pulling the loop. So rate of force, so power is equal to, and this is something you might know, or you can just look at what they said there, force times distance divided by time, which is the same as force times velocity. So, and we know they had to be the same units because we have power here and we're saying that's equal to something. Therefore, we're trying to equate this force to power, and to equate force to power, we multiply force by velocity. I know, a lot of dimensional analysis, a lot of understanding or memorizing of formulas. So for us, this is going to be L squared B squared times velocity over resistance. So this is the formula we're going to use. So I'm going to take this, copy and paste it, we move it down here, and we want to compare and contrast to what we just found right here. So the magnetic field we're going to look at here, the force, as we said, which is L cross B, what's going to happen here is we're going to have, we decided that current is going this direction, magnetic field is going into the board, so the cross product of L cross B, L is in the direction of current, so L cross B, this is going to create a force going down, this is going to create a force going up, L cross B, yep. This is going to create a force going to the left, this is going to create a force going to the right. So the bottom and top are going to be the same, just opposite directions, so they cancel out. Now, the left and the right are going to be different. They're in opposite directions, but the magnetic field at here, this will be a magnetic field, I'll call it initial. This will call a magnetic field at final. Those are going to be different, and so they aren't going to cancel out. So the only two wires that we're going to care about are going to be the left and the right ones. And so when we come back down here and we look at our magnetic field here, this is going to be the magnetic field at the left side minus the right side. So the force net is going to be, do this a little bit differently. I'm going to say here, I know this could have been done much cleaner. The force net on this square is going to be force on left wire minus force on the right wire, which is going to be I, because they're both influenced by the same current from that wire. They both have the same length, and it's just going to be magnetic field left minus magnetic field right. And so this down here, this B is going to be magnetic field left minus magnetic field right. So to write this out, and the magnetic field due to a current carrying wire, we already said it, this L means for line this time, not left. I know it gets confusing. Mu naught I over 2 pi R. Yep, mu naught I over 2 pi r. And so then this becomes, wait a second, did I miss something? Hoop. Aha, I did. So that's supposed to be v squared. F dt is force times velocity. Force is L squared b squared v over r. And then we pick up an extra v when we convert force into power. Okay, so that was a mistake. So that's supposed to be squared. So this is going to become L squared b squared, nope, v squared over r times, and then everything here is going to be constant that we can pull out, mu naught I over 2 pi, and the only difference between the b left and b right, so this here is magnetic field left minus magnetic field right. It's going to be 1 over r initial, because that's going to be the radius at the left side, the 9 centimeters. I'm going to call this r naught, and this will be r final. 1 minus r naught minus 1 over r final. And then that has to be squared. All right, so now we've derived the power that is dissipated in the resistance of this square, and we've also derived the power required to pull this square. And we want to see if they are the same. So we look at this, v squared, L squared, L squared, magnetic field squared, magnetic field squared, divided by r. So yes, these two are the same. And so the question was, in question B, find the electric power dissipated in the loop and show that it's equal to the rate in which an external force, yes, we just did that, pulling the loop to keep its speed constant does work. And so we could put numbers in and be like, oh, these two numbers are the same. But since we did everything in terms of variables, we're like, all the variables are the same. We plug in all the numbers, those are going to be the same. And that's how it works out. So to recap what we did here, because I know I went through this in the most confusing way possible, and I'm sorry. The first thing we want to do is we want to find EMF, electromotive force due to change in flux with respect to time. So we started with EMF equals negative d flux dt. Flux is magnetic field dot area, which in this case is basically magnetic field times area. We did an integral to find that. And then we took when we did derivative with respect to time, we did a derivative with respect to time. That derivative, we picked up a change in radius, or distance from the wire with respect to time, which is velocity, how fast it's being pulled away from the wire. That gave us an EMF, which is a voltage. We then said that voltage can be related to power. By power is voltage squared over resistance. And we're like, okay, this is how much power is being dissipated in our square. We then said that, all right, we have how much force is going to be taken to pull this square. So then we use two equations. Force equals QV cross V. But when you look at it more from a macro point of view, you can say that, well, all these charges are just electrons. These electrons are current. And so force equals IL cross B. We also have the formula that we usually memorize. Voltage equals LV cross B, or LVB. When we combined those and we used Ohm's law, we found that the force to pull is L squared B squared times V over R, and really this B here, since this is going to be force net is what we're concerned with, it's really going to be force on the left side versus force on the right side, and the only difference between the force on the left and the force on the right is the magnetic field. So this magnetic field here really becomes difference in B left minus B right. Then we want to look at force, convert force into power. To do that, we multiplied the force by velocity. Then we went down here, plugged in some more variables, compare and contrast, and we saw that they were the same. And that's the main idea behind this problem. Hope that helped. Bit complicated, sorry, but it's good to go through this and kind of have a general idea of how it works. Take care. See you next time.